This is the record of a major achievement in aeronautical science, a new technical breakthrough. It is the 10-year history of the development of the first jet-powered vertical takeoff and landing airplane possessing a design with a combat potential. For years, aircraft engineers have dreamed of a VTOL airplane with the high performance characteristics of conventional jet fighters, yet still able to land and take off vertically, regardless of surrounding terrain or local conditions. The Vertijet concept can eliminate the need for specially prepared runways for the long takeoff and landing runs needed by the latest jet planes. It also eliminates the need for landing gear associated with conventional takeoff and landing. Engineers saw tremendous possibilities if they could develop a jet airplane which would hover and rise vertically like a helicopter and combine this vertical rising capability with the flashing performance of the latest jet aircraft. Here in the picture which follows is the step-by-step development of the Vertijet, which culminated in the first complete demonstration of the VTOL capability of the Air Force's Ryan X-13 on April 11, 1957. The idea of vertical takeoff and landing using jet power was still in the Jules Verne category 10 years ago. However, engineers noted that the Ryan Fireball Jet Plus propeller fighters in the near-empty fuel condition developed thrust almost equal to weight. Given a little more push, and vertical flight could be an actuality. The concept grew as Ryan engineers traded ideas of how a VTOL jet should look and act. It was an intriguing problem, and Ryan sponsored further studies. The U.S. Navy Bureau of Aeronautics saw the possibilities too. In 1947, Ryan was awarded a contract to investigate the problems of a jet reaction type of control at near zero airspeeds where exhaust thrust rather than airflow over normal surfaces supplies control. Following studies, the jet engine was set up in a horizontal test stand and the practicability of this type of control was demonstrated. The next step was to place an engine with jet reaction controls in a free mount, which in turn was placed between vertical towers. This allowed checks of pitch, yaw, and roll control. In October of 1950, the remote-controlled test vehicle was lifted off the ground under its own power, demonstrating satisfactory attitude and vertical position control. Following these tests, the engine was equipped with shock-absorbing legs and an elementary control system. The towers were removed and tethering cables attached, which allowed horizontal and vertical movement of several feet. On May 31st, 1951, the world's first free hovering jet flight was made by the modified test vehicle. In 1952, the tethered test vehicle was again changed to incorporate a simulated delta wing, an approved control system with modified jet reaction controls, and greater freedom of motion. Development flight testing still continued, with the operator handling the vehicle from a remote control station. It was November 24th, 1953, that Pete Gerard, Ryan's chief engineering test pilot, climbed aboard the test vehicle and made the world's first piloted free hovering jet flight, using a temporary control station in lieu of cockpit and conventional controls. Second and most distinguished test pilot to accomplish free jet VTOL flight was Air Force Major General Albert Boyd of the Air Research and Development Command in the same vehicle. Paralleling this test work, studies of possible combat aircraft configurations were continued to point the way for test work and future planning. In February of 1952, the Navy had authorized extension of the study work into wind tunnel testing and preliminary design of a research airplane. This was the Ryan Model 38, which reached the mock-up stage. This mock-up, with its rotating cockpit, contributed valuable information for pilot environmental features, which were later included in the X-13 airplanes. At this point, the Air Force, with the complete cooperation of the Navy, initiated a revised research aircraft program with a contract awarded to Ryan in August 1953, calling for fabrication and flight test of the X-13 research airplane. Meanwhile, the Navy continued to sponsor the use of its modernized Delta Wing VTO test vehicle at the Ryan plant. This conversion, incorporating the new, more conventional cockpit, provided opportunity for component development testing and pilot familiarization in direct support of the X-13 program. Extensive free-flight wind tunnel and control line tests conducted by NACA at Langley Aeronautical Laboratory established feasibility of the techniques involved and provided valuable information on stability and control. With a model on the control line facility, transitions from hovering to forward flight and back to hovering were made. Vertical takeoffs and landings were made using wires stretched between poles. These tests were very successful and supported the results of extensive analysis done previously by the contractor to prove out the jet reaction control system to be used in the X-13. The X-13 is conventional aluminum alloy structure with the exception of the aft end of the fuselage, which is constructed of titanium. An unusual feature of this airplane is the large engine in relation to the size of the aircraft. Since a basic requirement of vertical takeoff is a favorable ratio between thrust and weight, a power plant producing considerably more thrust than gross airplane weight is used. Using electronic analog computer equipment, which duplicates flight conditions, two major flight simulation programs were carried out. One investigated the control system for transition and hovering. The other simulation included evaluation of the stability and control of the X-13 airplane in conventional horizontal flight. Construction of the X-13 had taken most of the time and attention of all concerned, but important work was being continuously carried on with the Navy VTO test vehicle. It was here that the jet reaction controls to be installed in the X-13 were first checked in vertical hovering flight. The piloting techniques of jet-powered vertical attitude hovering flight have proved to be relatively simple. This has been affirmed as a succession of Air Force visitors to the Ryan plant donned coveralls and tried their hands at flying the test vehicle within the limits of the tethering cable. It was apparent that any qualified pilot could learn the techniques involved after only a relatively few minutes of instruction. Even the most experienced of jet pilots got a thrill out of this new approach to flight. On July 13, 1955, the completed airplane was moved to the test area to begin ground engine runs. One month later, preliminary tests over, the X-13 left the Ryan plant en route to Edwards Air Force Base. A four-step test program had been outlined for the X-13 when the plane left for Edwards. First, the plane's characteristics would be checked out in normal horizontal flight with takeoff from the runway in conventional manner from a temporary landing gear. Second, the plane's hovering characteristics in the vertical attitude would be checked with takeoff made from the tail-sitting attitude using a temporary structure of tubing to support the airplane in proper position. Third, the transition in flight from the horizontal attitude to vertical hovering and back again would be explored at a safe altitude after takeoff in the conventional ground run operation normal for other jet aircraft. After all prior phases had been satisfactorily tested, the fourth and final demonstration would combine what had been learned to date. The X-13 would take off vertically from its ground service trailer, make the transition to horizontal flight, return to vertical hover, descend, and attach itself back onto the ground service trailer. And here is how the X-13 Vertijet program progressed. With pre-flight run-ups and taxi tests complete, the X-13 was ready for its first flight from Edwards Air Force Base. On December 10, 1955, the airplane made a short flight in conventional horizontal attitude. On January 9, 1956, the second flight was made. In a flight of over 20 minutes duration, an altitude of 16,000 feet was reached as the pilot tried out the aerodynamic controls. On the same day, an Air Force pilot made an evaluation flight and duplicated the performance. On the basis of these flights, the airplane was considered ready for continuation of the conventional flight test program to be followed by vertical flight testing. The tail-sitter type of temporary landing gear was used to expedite this vertical phase of test, with the Ryan-designed ground service trailer finding its first use to facilitate ground handling. It served to rotate the X-13 from horizontal to vertical and as an aid in maintenance and storage. On May 29th of last year, pilot Gerard made the first completely free hovering flight of the X-13. Vertical takeoff and landing tests had two major aims. The first, to evaluate the performance of the jet control system during vertical flight, and to adjust the various parameters to secure the best performance. The second purpose was to determine the maneuverability and handling characteristics in vertical flight, develop piloting techniques for hook-on landing to the ground service trailer, and investigate visibility requirements in approach and landing patterns. Stability, maneuverability, and handling characteristics were so excellent throughout the hovering flight program that major concentration was on calibration of control systems and the development of piloting techniques. Flying intricate and precise patterns at will and making spot landings within a tolerance of 2 feet became routine performance. At this stage of testing, precise control at minimum altitude rather than fast vertical ascent was the focus of critical exploration. Precision control during these most complex maneuvers presents a picture of rhythmic motion which caused one observer to refer to this demonstration as the Vertijet ballet. Initial investigation of the techniques required for approach and hook onto the ground trailer was conducted using a length of rope suspended between 2 towers. The simulated landing hook under the nose of the aircraft was constructed of plywood and hinged to deflect under load. Approaching in a slightly rolled attitude, permitting better visibility, the pilot contacts the simulated cable as he rolls parallel to it and reduces the thrust to engage the hook, thus providing a realistic assessment to his ability to perform the landing maneuver. On November 28, 1956, at a safe altitude above Edwards Air Force Base, after takeoff on conventional landing gear, the X-13 made the first jet VTOL transition from horizontal flight to vertical hovering and returned to horizontal conventional flight. In hovering flight, the airplane has neutral stability, which manually controlled would require considerable attention by the pilot. The control system acts to simplify the pilot's task and increase the accuracy with which the airplane may be maneuvered. The usually invisible column on which the X-13 is supported in vertical attitude can be seen in this flight. This stream of exhaust gases has a static sea-level thrust of 10,000 pounds and a nozzle temperature of 670 degrees centigrade. The X-13 is itself a milestone in aviation history. It has proven itself in all phases of development: conventional flight, hovering, transition, and complete VTOL mission. The operational advantages of jet VTOL aircraft are numerous. In Air Force tactical operations, they may be deployed anywhere in the world with a degree of mobility and dispersion not presently attainable with conventional fighter aircraft. At sea, task force speed and maneuverability will be increased, since launch and recovery may be initiated with any wind direction and reasonable velocity and from many types of combat and support ships. The speed range of the Vertijet makes it impossible to fly chase on the X-13 with conventional aircraft. The helicopter makes an excellent point of reference as the Vertijet flies formation during complete transition. In exit transition, however, the helicopter is rapidly left behind. As one test pilot at Edwards has phrased it, the only airplane that can successfully fly chase on the X-13 is another Vertijet. After transition to and from the vertical has been thoroughly investigated at high altitude, the pilot brings the X-13 down to minimum altitude in order to practice approach and landing patterns in proximity to the ground service trailer. Followed by transition into conventional flight, which permits acceleration up to speeds of some 300 knots. This is conventional landing on the lake bed at Edwards Air Force Base using the fixed tricycle landing gear. Now the somewhat nose-high touchdown, typical of delta wing aircraft. The drag chute deploys to assist deceleration, and the flight is over. On April 11, 1957, the X-13 was in final configuration. Landing gear removed.